So good afternoon, everybody. It's my pleasure as the director of the Erwin Schrödinger Institute to welcome all of you to the first ever award ceremony for the medal of the Erwin Schrödinger Institute for Mathematics and Physics, or in short, the ESI medal. It's great to have you all here, either in the lecture hall, and I see that there are many people attending online. That's great to have you all here for this very special occasion. Let me extend a particularly warm welcome to the members of the Scientific Advisory Board of the ESI, who have done very important work for this prize. And of course, I would like to welcome the recipient of the first ESI medal, Professor Anton Alekseev from the University of Geneva. Now, of course, we had planned to have Anton here at the Schrödinger Institute for this celebration, but due to the travel advisory that Switzerland has issued recently for Vienna, he unfortunately couldn't come. Now, since we don't know when travel will be possible again in a normal way, we decided to go ahead with the ceremony, and I'm very glad that Professor Alekseev is able to join us online from his home in Geneva. Now, these are very unusual and weird times. The pandemic has turned upside down the lives of many of us, and it has, of course, also affected the life here at the Erwin Schrödinger Institute. Last year, we had more than 1,000 participants in the various activities of the Institute, in the workshops, in the thematic programs, in the senior and junior fellow program. So we really had many people coming here to the ESI and enjoying the nice atmosphere here at the Institute. And this went on, of course, January and February of this year, and then the pandemic came over us, and there was a complete lockdown. The ESI was essentially closed from March to July. We started to resume some activities in August at a very low intensity, and have continued until now. For the rest of the year, after this ceremony here, there won't be much going on at the ESI in person. But of course, we have learned as a community how to keep in touch and to continue the discussions. And so a number of activities at the Erwin Schrödinger Institute have been taking place online in a virtual space like this ceremony today. So I'm very glad that we can have this ceremony today for the first ever ESI medal. So let me just explain a little bit about the ESI medal. So the ESI medal is a recognition for outstanding achievements in the fields of research in the scope of the ESI. So this now includes all of mathematics and physics, while initially the scientific focus of the ESI was mathematical physics. Now it includes all of mathematics and physics, and this is also, of course, the scope of the prize. We wanted to create a focal point for the ESI community, also the possibility to have a nice party once a year to come together as local and international ESI community. Now, we can do this, of course. This big party won't happen this year, but I hope that it will happen next year and in the years to come. So we started discussing the ESI medal about 2 years ago. We set up statutes. If you are interested in the statutes of the ESI medal, you can go to the webpage of the ESI and look them up there. So once that was done, we had a call and had nominations. And then the Scientific Advisory Board of the Erwin Schrödinger Institute, chaired by Professor Miriam Cvetic from the University of Pennsylvania, went to work and selected the first recipient of the medal. So I would like to thank the Scientific Advisory Board of the ESI for doing this very important work. And they made a very good choice, I think. So today we celebrate the award of the ESI medal to Professor Anton Alekseev from the University of Geneva. And Professor Thomas Strobel will tell us more about the life and the work of Professor Alekseev, so I don't need to say much here. Let me just point out that Professor Alekseev, you see here in the background, has done very important work in a range of subjects, including algebra and geometry, mechanics, and field theory. So I think that Anton Alekseev is a leader in his field, and he has certainly set very high standards for the ESI medal in the years to come. So I'm very happy to be able today to award him the medal. Before I give the stage to Professor Strobel, let me just mention to you that Professor Alekseev is also an old friend of the ESI. He was a postdoc here at the Institute in 1993. This is the year when the ESI was actually founded. And over the years, he has participated in many activities. He has been a senior fellow at the Institute. He has organized a number of activities. So I'm very glad that we can give the medal to an old friend of the ESI today. This, of course, didn't play any role in awarding the medal, but it's a nice side effect, nevertheless. So before I now turn the stage and the screens to Professor Strobel, let me explain the procedure for today. So Professor Strobel will give the laudation of Professor Alekseev, and then there will be some music. Then I will hand the medal to Anton. Then there will be some, Professor Alekseev will give a scientific talk, and after that there will be also some music. In between, we will have a short break so everybody can stretch their legs and go to the fridge if you are at home. Okay, so having said that, I would like now to ask Professor Strobel to the stage and give his presentation. Please.
It is my honor, but it has been also a heavy duty to give this honorary speech for my friend Anton. And for those who don't remember how he looks like or never have seen him, this is my friend Anton, the recipient of this first beautiful idea of a medal. And he received this medal for enormously beautiful work within the last 10 years. And in the center of this work is the Kashiwara-Vergne conjecture, which he proved first with Eckhard Meinrenken in 2006 or 2007, and then later in 2012 in another way with Torosian. I will say a little bit about this in the talk also. And it is related to a variety of other subjects like the Gelfand-Zeitlin integrable models or the Horn problem about eigenvalues of matrices. And there's also an idea about tropicalization of Poisson geometry and Lie bialgebras in Goldman-Turaev, about loops on surfaces, associators, and so on and so on. It is a landscape of very different subjects in mathematics, starting from geometry and algebra, but stretching out to topology of loops on two-dimensional surfaces, even to number theory. And this work has been also largely recognized. He was invited to give a talk. This is nicht ganz da. Gave a talk at the ECM, at the ICM. He had publications in Annals of Mathematics, several ones in Invenciones, and so on and so on. And yes, and this is also something which was mentioned already a bit. It could be hardly someone better to have received this prize, because also he worked in physics and mathematics. And even in the last 10 years, he still published some things in communications of mathematical physics, letters of mathematical physics, and even in JHAP. So I put these journals here too, because he also does still contributions, makes still contributions also in pure physics. And these are, I have to say, very, very high mountains, and I tried to climb a little bit in there, and they're very, very steep, and I tried to do my best, but I got a bit scared, and even if my friend Anton from time to time tried to help me, I thought it is, maybe it would be better someone else could explain this work, and I want to promote again the idea that maybe you can invite next year some people, some experts in the field who explain this a bit, because it's a beautiful landscape and I'm an admirer, but I don't feel so well in these heights. So I decided to talk about the story before. So it shall be a kind of a personal perspective. I know Anton since a long time, and you know, everybody in the end of the day cooks with water. So the things he uses now, they all had their sources somewhere, and one can see that, and I will try to pinpoint my finger to where it happened. So, es geht nicht ganz gut. Stop. No, sorry. I'm new in this system. It's my first talk in this fashion. Okay, so I met Anton in Les Souches in 1992, and these are beautiful mountains, a beautiful school, very clever people there. It was amazing. And let me zoom a bit closer. Here you see Anton as a young and me next to it. And yes, if you observe the same as me, at that time, or let's say like now, he lost a lot of hair, and I, in contrast. Right. So, but I agree that this is not the point of this talk. It's not about me. It's about my friend Anton. And so let us start where everything began. And this was in St. Petersburg in August 1967, where a star was born who later will have many followers. And you will also see and understand why. So here he was his education, and there are two very noteworthy places. One is this Lyceanum 239, which also had a lot of other great people, like Perelman was there, for example. And the Steklov Mathematics Institute, which also played an important role in the early stage of Anton. And let me say a little bit about this Lyceum 239. So this was apparently an incredibly good mathematics teacher there. So instead of teaching theorems and proving them in front of the pupils, he asked them to prove everything themselves. So he kind of made a statement and said, prove it. So they didn't see any proof. They had to prove everything themselves. And many people, like including me, but not only me, noticed that Anton was like in advance and super fast and sharp in many, many things. And so the experience already then people made was about like this. And I want to say a small anecdote, which I learned from a pupil of the school of Anton. So apparently there was a mathematics exam, and this mathematics exam was taken by Perelman, who was a bit earlier in the school. So he came back to give an exam. And the task was to solve 10 problems and to present the proof for each of these problems. And when you couldn't prove it or you were too slow to prove it, there was a fixed time and you should see how many of these 10 problems you can solve. And I talked to the person who was the second best. and she solved 2.5 problems. And now guess how many Anton solved? 10 out of 10. So this was the experience many of us made later as well. Amazing. And this happened in a very, very early time already. So here, thanks to Leonid for finding this picture. This was in the Physics Olympiads 1984 when Anton was 17 and won the first gold medal in physics in the Soviet Union. And it followed, or actually one was before, also 2 international gold medals in the Physics Olympiads. So this was an important part of Anton's life, and in '84 he came to the university, and not much later he published his first paper, and here is the English translation. And it's amazing, he was like 19 years old when this paper was sent to the journal, 19 years old. I was always so astonished. I had a kind of queer career. I started with 21 to learn the first things about physics. And he had already a paper about anomalies in Young-Mills theories and fermions, so quantum field theory. So this is, for me, this was always amazing and like characteristic for Anton in his speed. And then there were several papers which actually paved the way also to his current research. And one of those was about the quantization of symplectic orbits on compact Lie groups and using the functional integral method. So this was a beautiful work of mathematical physics, and I decided to devote a little bit to tell you a little bit about this. And there should be, I think, one part also where I try to address physicists and mathematicians at the same time. So it will be slightly elementary, but I want to make one point, which you will see. So let me give you the mathematical setting to the story. So let G be a Lie group, and let's call frac G its Lie algebra. Then there was a famous method initiated 20 years before Anton arrived, around his birth, which I think was initiated by Kirillov, which related the representations of a Lie group G with the coadjoint orbits of the group acting on the dual of the Lie algebra. So there's a natural action of the group acting on a Lie algebra and thus induces one on the dual. And to be honest, actually it is the quantization of these orbits which is in some way very intimately related to representation theory. And the people in the game were Kirillov, Kostanz-Ryau. And one thing in this context which was important, which was an important question posed by Kirillov, is related to the character of a representation. So let me just briefly recall, what is a character? Suppose you have a representation rho of matrices like representing a Lie algebra in some vector space V, then you can take the trace of these matrices, and for each group element you obtain a complex or real number, depending on if it's a complex or a real representation. And Kirillov gave a beautiful formula for this. So suppose X is an element in the Lie algebra, you can take the exponential map that gives a group element and calculate the character. And he said you can integrate over these coadjoint orbits, which I will explain a bit more in a second. So Y is a point in this coadjoint orbit. Here is Y is an element in the dual of the Lie algebra. So you compare it with X inside the Lie algebra. This gives a number. You take the exponential. You integrate over this coadjoint orbit. And then there is here a Jacobian, which measures the difference, or the square root of it, the difference of the measure on the Lie algebra and the Lie group. So you have this kind of Jacobian of this, some diffeomorphism there. And Kirillov asked the question, so this is a kind of classical formula, but is there also a quantum version for this? And one possible way of quantization would be the path integral. So, and this question was answered by Alekseev with two other outstanding mathematical physicists, Samson Chatashvili, who I saw is present, and Ludwig Fadeev, who was a great teacher of both of them, I think. And let me now explain a little bit the ingredients to their work, so a bit like the starting point. I will not go through the details of this paper, but what is the setting? What are the things Anton knew in this very early age, like kindergarten or something? Okay, a bit later, but like when I had no idea what the group was or what the quantization would be, he knew all this and even made a famous publication about this. So one of the ingredients are Poisson manifolds. So what is a Poisson manifold? It's a manifold equipped with a bracket on the functions, which is a Lie algebra, so it's an infinite dimensional Lie algebra, and which satisfies this Leibniz rule. So if you have the product of two functions and you take the bracket of one function with two other functions like this, then it differentiates f and g. So that's a Poisson algebra or Poisson manifold. We are used from physics to this concept, but there it's a bit special. I will give this as my first example. But note also you can put, for example, the zero bracket. It also satisfies this. It's something in physics would not appear. And in fact, what the relevant Poisson brackets will be in between these two cases. So the first example is the one from mechanics, where you have the cotangent bundle of a configuration space, T star Q, and where you have variables Q and P. And then this bracket is defined by this formula, which every physicist knows. So it's a sum over the derivatives of Q and P and antisymmetrized, and which satisfies these axioms. And behind all this is a symplectic form. So this corresponds to bivector field, and its inverse is symplectic form omega. And note that this symplectic form is exact. So it's the ramp differential of a canonical one form that one can define on T star Q. A very different example arises if one looks at the dual of a Lie algebra. How does this work? So let's take two elements of the Lie algebra, Xi1 and Xi2. Now, the dual of the Lie algebra, the dual of the dual is again dual to it, so these elements can be viewed as functions, linear functions on G star, right? So we should define a bracket on all functions, but let's define it first on linear functions. And there we can just take, because Xi1 and Xi2 are Lie algebra elements, we can define it to be just a Lie bracket of the two, which is again a function, a linear function. And then we have the Leibniz rule to extend it. So we know it now in a coordinate system, so we can extend it. This has, in general, a very highly non-trivial, induces a highly non-trivial geometry. So let me just illustrate it in the simplest example, where G is SU2, so G star is on R3. So we have like three coordinates, X, Y, and Z. And then this bracket induces symplectic manifolds, which are actually spheres. So concentric spheres on the origin. So these are symplectic manifolds, and they carry this famous Kirillov-Kostan-Soriot symplectic form. But since this is a volume form with this two-sphere, it cannot be exact. So this will play a role in a second. And yeah. So the second ingredient are path integrals. So this is something which in mathematics in principle is not defined at all. So this is an integral along the paths of a particle, in this case, Q and described by Q and P, the coordinates in the cotangent bundle, say. And it is an art of physics or mathematical physics to give this a meaning. And it's one way invented by Feynman to quantize a theory. And in the simplest case, here is the classical action. Let us look at the Hamiltonian classical action. So it starts with PQ dot and then minus the Hamiltonian of the system. And it's always at t, and this is an integral over an infinite dimensional space of paths, in some sense at least. Note that here you have this, this PDQ actually turned into PQ dot, so this D turns into dot. So you need to define it as it is, you need this PQ dot. And let me make a remark also that if you have a gauge theory, then the situation is slightly more complicated. And Anton's teacher, Fadeev, actually was an important person in this context to give a meaning to the path integral and the quantization in the case of gauge theories in the context of Fadeev-Popov ghosts. So, however, as mentioned before, on these orbits inside G star, this is not exact, so we don't even know what to put here. It starts here, the problem. And the way out is to replace, in some sense, G star by the dual of the Lie algebra, by the Lie group. This will be a recurring theme, as we will see. So let us be more precise. Let us fix some element in a coadjoint orbit. So suppose in SU3 you take some vector in SU2 star, sorry, this R3, you take some vector on the 3-axis of some fixed length. Then the length fixes the orbit, and then you can obtain the whole coadjoint orbit by acting with the group elements by the coadjoint action. In the case of this vector in R3, this just generates all rotations of this vector, okay? And so you can get these spheres in this way, but now G is an element in all of the group. That also means that there are some parts of G which will drop out. And what part is it? Actually, it's the stabilizer group, which I recall its definition here. So all these elements which satisfy that H inside G such that H inverse BH is equal to B. So the coadjoint action of H on B doesn't change B, because then you can write G as H times G tilde, and you see that if you have this equation, this H drops out. That means that actually you have the quotient of G over H, and this implies that now we are actually dealing with the gauge theory, because instead of loops inside the coadjoint orbits, we take loops inside the group. And then, however, we have some equivalence, because this subgroup H has to be factored out. So we are dealing with a gauge theory. And now let me turn to the answer of these three people. So in the case that G is a compact Lie group, they say that the character of exponential of x can be obtained by a path integral, to which they gave some meaning with some regularization and a lot of very brilliant technical tricks they use. With the following action. So G now is an element in a group, but a path. So in the path integral, you also need boundary conditions. They chose periodic boundary conditions. So it's a map from S1 to the group G. Now X is already fixed, but now fix this some B also inside the coadjoint orbit, like this vector in the 3 direction in R3. And then the action takes the following form. So you have B is in the dual of the Lie algebra, G inverse G dot can be viewed as a Lie algebra valued one form on the group, so you can pair it with B. And this was the way out for this PQ dot. So PQ dot was a primitive. Actually, if you pull it back to the group, it does become exact. And there you can write such a term. And then here you have a second term, which depends on this X. And it should be viewed as the Hamiltonian of the system. So this X actually fixes the Hamiltonian, okay? And this is the beautiful formula they found, and this model continues playing an interesting role henceforth. Note also that while the original formula of Kirillov had an integral, finite dimensional integral, or a path integral. It had in front some function of x, and here there's just a constant which you can normalize to be 1 in this process of giving meaning to this integral. So there's no correcting function here of x, so it's just as it stands. So it's in some way very beautiful, and actually a year before this, Anton and Samson Shatashvili, they published another paper where instead of looking at coadjuvant orbits in compact Lie groups, they looked at an infinite dimensional group, namely the Virasoro group, the group of different physics of a circle centrally extended, and took the coadjuvant orbits there. And this paper actually became very, very famous in the last years, and if I understand correctly, Anton will talk, I hope, if it hasn't changed the plan, he will talk about this in his speech. But, so this is amazing work. And so now, all this was before we met in Les Souches, and so here's my friend Anton, if I'm not mistaken at least, and here I am on the other side of the world, and it may have been, although we understood each other well when we met, it may have been that it would have stayed like this, we would have separated in different corners, if not something special had happened a year afterwards. And this was this wonderful idea of a very big person in Vienna, Walter Thierry, together also with other people like Peter Michor and Mr. Reiter, and who helped realizing this vision of Professor Thierry to establish a center of mathematical physics, which now is enlarged to cope all of physics and mathematics in Vienna, and which was really a very lucky incident, I think, for the city. And I think he made a very, I want to also mention that Thierry was a very important person to me also, because he was a kind of existence proof, and he was like one of those persons I really could admire when I was a student. And it was not so easy otherwise, because there was a kind of desert after the Second World War. All these great people had disappeared, and there was one who really was outstanding and an extremely good leader and teacher. And this is a picture, I think, when he was 80 years old, and still you see his visionary look, and I think he made an extremely good job to create this institute. And so this was in 1993, and as mentioned already in Christoph's introduction, Anton Alekseev was one of the first postdocs, or I mean, there were two first postdocs. It was Anton and Volker Schomeros. And here is Anton, and I thank the people who helped me producing these pictures out of some video. And with Volker actually, and in the beginning also Harald Grosse, they started the whole program at the ESI of very interesting work, like about the quantization of the Chern-Simons theory, which combined in a very beautiful way questions of physics with very advanced mathematical tools, and they made some classification of quantum groups and so on. They used all tools which Anton learned in this School of Integrable Models. And later they had beautiful work on D-branes, which also would be very interesting to talk about, and which has been very highly recognized in string theory. However, I thought of sticking to the line of talking more about my interaction with Anton. So Anton came back in January '94 to the ESI. And maybe it was January or February, I don't know, but something like this. And actually already before, in September '93, he had organized a conference in Finland where I participated. And we wrote up some, with Peter Schaller, we wrote up some paper for the proceedings contribution. And that was our first paper about the Poisson-Singer model, not the one which you cited, there was an earlier, which was that. And when Anton came, I handed him this paper. And it was in the evening at the Technical University, if I remember correctly. And he came back the next day, and he understood at once that this was an important thing. And he made me being invited to the Schrödinger Institute to give a talk about this. By the way, Thiering also invited me in the end of '93 to talk about this. So this, he understood this right away, but even more, he asked a question. Namely, he was in his school with Ludwig and Samson. He was exposed a lot to the WCW models. Again, there was a group there, and the joint actions on the group. And inside the Poisson sigma model, a special case were BF theory. And BF theory depends on a connection. So it's a Lie algebra valued one form. We will come back to this at the end of my talk. And a G star valued function B. And in the G over GW, it's a double model. You have this also a connection, but now you have a group element. And so he asked the question, can we not replace the dual of a Lie algebra again by a Lie group in this context, which means replace B by G. And that led to, actually I should say something else. So he proposed this to Peter and me, and the next day Peter and I tried to understand what this model would be. So we spent the evening trying to understand it, and we met the day after Anton again, and Anton asked, so did you make some progress? And I said, okay, yeah, we understood the problem. And then he said, and then I said, but we didn't, okay, but we were starting with it, so we didn't make really progress in it. He said, it doesn't matter, I solved it. So, and he showed what he probably learned in kindergarten, the Gaussian decomposition of groups, and he produced some Sklianin bracket from there. And that was the starting point of a joint publication where Peter and I also had our contributions, but more slowly. And but it showed like how extremely fast he is, and it's a recurring theme in many experiences, not only I make. Maybe there's some more remark which can be made, namely that this picture that this G over G WCW model is a Poisson sigma model worked almost everywhere. There were some parts of the group had to be cut out. Then only later it was noticed that if this was not invented at the time, like Poisson, twisted Poisson structures and even Dirac structures. So in the twisted Poisson case, you can cover a bigger part of the group, but still not that. And with the Dirac structures, you can really cover this. And also Anton made there some contributions of studying those. Let me mention that the paper we wrote together was called Generalized Momentum Representation, because in this theory here, these were the momenta of the coordinates. So this was this P and this the Q in the theory. And now this P, this momentum, was replaced by a group element. And that became later an important thing in Anton's work, namely when he introduced with Eckhard Meinrenken and Malkin, I think a student of Anton, the group-valued moment maps. So the starting point is symplectic reduction, and it's called moment maps because it contains momenta in this case. So you have a map, you have a group action on a symplectic manifold M omega, and if you have some symmetry, so this leaves omega appropriately invariant, then this can be expressed as a map to the dual of the Lie algebra, which is a covariant, or a Poisson map, which is the same thing. And this is the moment map, and there are important theorems about this. One of these theorems is Marsden-Weinstein reduction, which is the mathematical reformulation of what physicists do when they go to the reduced phase space. And this is if you choose an element here, a point here in G star, which is regular, and then you take the pre-image of mu, so these are the constraint surface in the language of physics, and you integrate out the stabilizer inside here, you get a symplectic manifold again. So that's a mathematical theorem, and there are many more interesting related mathematical theorems, like about convexity, like localization formulas like Dusterman-Heckman, and so on. So this is a beautiful thing, and Anton posed the question if maybe here he can replace G star by G. And this indeed turned out to be possible, and he provided with his co-authors a very nice dictionary. And I just want to highlight the first formula. So instead of d omega equal to 0, omega being symplectic form, being closed, here you on the group, you pull back, the group is, say, same as simple, compact, you pull back the canonical free form which you have there, and you say that d omega, by this map mu precisely, which you have in the game, and you say that d omega should be the pullback of this H. And then they have a theorem that, again, if now you take a regular value in G, then this new quotient, where this is the stabilizer of the group element by joint actions, is a symplectic manifold. And this is actually interesting in very different ways. Can we make this visible here? No? Okay, doesn't matter. So one important application is if you look at the moduli space of flecked connection on a Riemannian surface of handle H, which is described by holonomies along some loops, non-contractible loops, up to conjugation by G, with values in G. So you get 2H such group elements, and you need to take the quotient. Then you can show that actually this moduli space can be understood as a symplectic reduction in this more general context of the group valued moment maps. And if you just look, there's usually one relation. If you represent this genus H surface by this polygon, then there's alpha 1, beta 1, etc. are non-contractible loops generating the fundamental group. Then there's usually one relation between them, namely that they add up to the identity. So if you look at the holonomies with the corresponding letters A, then this product should be the identity. And now you see there's the identity in the group, and that actually is precisely this moment map in this context. So this is again a scientific part, so I thought I should come back also to some personal issue in this context. And I listed some of the students of Anton. I don't know if this list is complete, probably at least one I forgot. So there are a lot of students, and some of which, like Florian Neff, but many more probably have a permanent position already somewhere. So Anton really is a leader in the field, as was mentioned already before. He also had like at least 13 postdocs, and he organized so many things, it's just unbelievable. And Anton is also very generous in this context, and if someone gets stuck, he does help out. So thanks to Eckert for this nice picture. That's his wife having troubles with the water. And you see there's some space left, and I still should say maybe some words about the curriculum of Anton. So I thought I put this here. So starting after his PhD, which he finished in 1 year, he was 2 years at the Stekelhoff Institute. He was at Uppsala University, then at the ETH with Jörg Fröhlich, and then again at Uppsala University, where in the end he was a professor for theoretical physics. And in 2001, he completely turned mathematician and at the University of Geneva. And so the final thing, I wanted to close the circle, come to something which happened just precisely before the work for which he won the prize, and these are the so-called Alekseev-Tarosian connections. So let me just explain you what those are. So for connections, a Lie algebra valued one form, we need first a Lie algebra. The Lie algebra here is an infinite dimensional Lie algebra, and it is generated by trees. So you can just really imagine a tree. So it has some trunk, it's called trunk, I think so. Some root, if you want, rooted trees in mathematics. And then there are the branches and the leaves. And the leaves, they can have some decoration. So the root and like everything which goes out of this graph of this tree can have some numbering from 1 to n. So n is some fixed number, and for each n you get such a Lie algebra. So this first the vector space. You look at all these trees. So there are infinitely many. So there's an infinite dimensional space. You take for each of them, you take as a generator of a vector space. You multiply it by some numbers if you want. But then you need to take a quotient. And one of the quotients is, for example, if you have the tree like. If you flip the tree, if you make a mirror, so this A and B, there can be some complicated thing. If you flip it like this, you get a minus sign, and there's a more complicated other quotient. So this is the vector space of this Lie algebra, and then there's a Lie bracket, and I depicted the Lie bracket for two very simple trees. And whenever you see that such numbers coincide, like the one here, then the bracket, the Lie bracket between these two basis elements in this Lie algebra is constructed by some composition of this graph with this graph. So you kind of glue this one to this, but then you keep still the one which goes out, and you get from these two, you would get this one. And there are many more complicated ones. If there's like several ones, then you have to glue all of them together. You get some signs, plus, minus, and the whole sum of those on the right-hand side. Then you can prove that this is a Lie algebra. Second, you need a manifold. And the manifold here is called configuration space of n points in the complex plane. So you take Z1 up to Zn in the complex plane, and you require that if they coincide, they must not coincide. So you cut out all these diagonals. And then they defined a connection in the following way. So you sum over all possible trees. So it's an infinite sum, but this Lie algebra is graded. So in each degree, you have a finite number. So the sum is very well defined. So you sum over all trees, and then there you need some one forms. So the trees live in the Lie algebra, but you need some one forms living on M, and they are constructed in this example like that. So you have, suppose you have a tree like this, then the first step you replace all the leaves by variables Z1 up to Zn, and you also do a similar thing for the internal vertices, W1 to Wk, and then you have an integral over these internal vertices, so over these W's, and you integrate one forms which are the arguments. For example, here from this area you get Z1 to minus W1, so this is the one corresponding to this arrow, and you have 1, 2, 3, 4, 5, and this is a four-dimensional space, so you just get one form, which is precisely what is needed. So this is a definition, and it is far from obvious, and it's a theorem of them, that this is a flat connection. It's a long proof, but however, again, everybody cooks with water. There's some kind of intuition behind, which precisely Anton masters in a very good way. So there's a BF theory behind this game, and this equation can be viewed as a quantum equation of motion in some topological quantum field theory. And this leads me to at least the words of mentioned in his in the work he did in the last 10 years. And this led precisely this connection, this flat connection, led to a new proof of the Kashiwara-Vergne conjecture, which was a conjecture from 1978, which he had proven with Meinrad in a geometrical way, and now he proved it in a purely algebraic way. The second thing, it was related to associators in algebra, in particular the Dreamfield associator, and there was another associator which came from the parallel transport of this connection, this infinite dimensional space, and these are now called the Alekseev-Torossian associators. So this brings us back to the initial slide where we started from, and I want to end with a small personal anecdote. So like many, many years ago, somewhere in the 90s, my father asked Anton, what is his goal? in life? What does he want to achieve? And apparently, I don't know if they were talking in some metaphors, but Anton said, I want to become a general. And I think, Anton, you really succeeded. You are a general, and for this also you're awarded a medal now. And even more, I think you're an emperor of a very beautiful country in science, which is all yours. So congratulations from my side.
Well, thank you very much, Thomas, for this beautiful talk, for this beautiful appreciation of the work of Anton Alekseev. I actually watched Anton a number of times while you were talking, and he looked pleased. Sometimes I think he even nodded approvingly, so you did a great job. What I also liked about your talk is that you showed how the ESI has an impact. The encounters, the discussions that happen at the ESI have an impact on the career and on the science, particularly of young people, so I think this is really great. Okay, so welcome to the second part of the ceremony. We will start with some music. May I ask the musicians to the stage? Actually, Teresa Kalchhauser, who is not only an excellent musician, but also works in the administration of the ESI, and Wolfgang Augustin are going to play one movement of the Sonata for two violins by Georg Philipp Telemann. Please. Thank you very much. This was beautiful. And now we come to the big moment. I will present in a moment the medal of the Erwin Schrödinger Institute to Professor Anton Alekseev from the University of Geneva. He will get this medal. Let me read the citation. Professor Alekseev is honored for his recent outstanding contributions to mathematics, in particular for the discovery of the link between the Grothendieck-Teichmüller group and the long-standing Kashiwara-Vergne problem in Lie theory, for the program of tropicalization of Poisson structures, and for the proof of the Goldman-Turaev formality in two-dimensional topology. His work unites brilliant intuition, deep knowledge, and remarkable technical skills. And for this work, he will receive the medal of the ESI, of course. So let me show the medal. Can you actually show the next slide, which shows the medal? I have it here, but it's actually too small, I guess, if I show it into camera. So we have prepared a slide. The front of the medal shows Erwin Schrödinger in a pensive mood. Actually, it's the same pose of Walter Thierry in your talk, Thomas. right? You showed the picture of Walter Thierry, actually looks similar. So the front shows Erwin Schrödinger, and the text is a medal of the Erwin Schrödinger International Institute for Mathematics and Physics. That's the official name of the institute. And the back just shows the logo of the ESI. The medal was designed by Philipp Steinkellner, and I must say that I like it a lot. So Professor Alekseev will not only get the medal, he will also get a nice certificate. The certificate is here. It is some nice certificate for the office wall, I guess. And it's signed by the chair of the Scientific Advisory Board of the ESI, Professor Miriam Cvetic, and by myself. This is not all. There is also a financial award that goes to the recipient of the medal, and I would like to thank the Association of the Erwin Schrödinger Institute for contributing to the monetary award that the recipient will receive. Okay, so now perhaps you can switch, because using physics, I'm now going to hand the medal, which you can see here, to Professor Alekseev in Geneva. Are you ready? Yes, he is ready.
Yeah.
So I'll close the box, because otherwise, you know, just for safety. And I will now use something that our experimental colleagues helped us to put together, and I will pass the medal over to Geneva. Does it work? Yes, it seems to work. So if teleportation does not work between Vienna and Geneva, then I don't know where it should work. Unfortunately, it turned out that the certificate is too big for the teleporter. So at some point, Anton, you will have to come to Vienna to pick up your certificate. And when you come, I will also be very glad to take you out for a nice dinner. So I think it's now time for you. Finally, you can say something. You have been very patient for a long time, and now I ask you to give your talk, please.
Okay, thank you very much. Let me start with thanks. So there are so many things I want to say. Well, of course, I'm so sad I cannot be with you in Vienna at the Schrödinger Institute, but I'm so happy that I'm with you on Zoom and so many people could come. So I see so many faces that I know. So I'm honored and flattered by the award of the ESI medal. And I would like to thank many people, of course, first of all, the Schrödinger Institute for creating the medal, and the committee for awarding it to me. I don't know whether it's a good decision, that's for you to judge, but I'm deeply touched. So I would like to thank Thomas Strobel and Chen Changzhu, who nominated me for the medal, and Thomas for his wonderful and very touching talk. I would like to thank my collaborators. You know, you listed some results, and I didn't obtain them alone. There were many people who helped me. I don't know to what extent it is it's just that I'm getting the medal, but I thank you all for your collaboration. You're all brilliant people, and I'm honored to work with you on those interesting problems. So I would like to thank all the collaborators, colleagues, and friends who are present at the ceremony, and of course my family who were always supporting me and who are here with me now. Maybe before diving into some mathematics or physics, already on the chart, there was a suggestion to give some anecdotes about the Schrödinger Institute, and I would like to follow this advice. Thomas already mentioned that I joined the Institute when it was basically starting. It was in 1993. So let me give you some short stories about that time. There is a notion of good old time. Of course, it makes more sense when you get older, right? So then the time which happened before becomes good old time. But I think really that time qualifies, that time at the Schrödinger Institute in particular qualifies as good old time. I arrived in March 1993. That was my first time in Vienna. I got a 4 months position as a postdoc at the Schrödinger Institute. And, it was an institute like no other institute. Of course, I didn't have that much experience, so I couldn't judge that much. But to start with, the first week was a conference, and it took place in some castle. I don't quite remember by now what castle it was. It was a very impressive place. And then, as many of you know, but perhaps some of you don't know, the institute was situated in 3 apartments in the building just opposite to the Hotel Strudelhof Palace, nearby the current location of the Schrödinger Institute. So actually, that was the building where Schrödinger lived himself when we returned to Vienna from Ireland after the World War II. And, when the institute is located in apartments, it makes an impression of a family. In the evening, Italians would cook at the kitchens which remained in the apartments and would give food to postdocs which would be wandering around. That was a very, very interesting and exciting time. So I got there as a postdoc, I think, thanks to recommendation of my teacher, Ludwig Fedeev, and Ivan Todorov. So they recommended me, and I was accepted. And then there I had a chance to meet Walter Turing. He was coming from time to time to check up how his institute is doing. And then, of course, Peter Michar was the director, and he was looking at the everyday activities of the institute. So my postdoc mentor was Harald Grosse. And Thomas already mentioned, so Volker Schemerus, I actually knew him before, but not so well. And we met there as postdocs of the Schrödinger Institute, and we started collaborating, 2 of us and Harald Grosse, and it gave rise to some kind of very exciting for me activity, which actually, what's interesting, we'll have another occasion to mention it, but there are those waves. So topics, they become fashionable, and then everybody forgets about them. But if the topic is reasonably good, after some time, it comes back. And that topic, this quantization of moduli spaces that we were developing with Harald Grosse and Volker Schemerus, now it comes back in a somewhat different disguise. And that's very pleasant to see that those things, they are mostly correct and they remain interesting. I met Thomas Strobel before at the Lizouche School, but because of those days at the Schrödinger Institute, we started collaborating, and this collaboration continues now. I also met a PhD student of Peter Michar, Cornelia Wiesmann, and then also we started an exciting collaboration, which later on gave rise to a research paper. So it was a very, for me, at least for me, this good old time means that many things in my life and in my career, they were influenced and decided by the stay at the Schrödinger Institute. So that's why it's important for me that this award comes from the place that I feel like home, at least in some way. As I said, it was a good old time. but the Schrödinger Institute continues to impress us. So now it's a good new time. So I thank again the Schrödinger Institute and everybody involved for this award. And I would like perhaps now to entertain or to bore you a little bit with mathematics or physics, depends how you consider it. And, you know, I decided to give a somewhat mysterious title to my talk. It's called From Algebra to Geometry and Back Again, looking for the South Pole. At the moment, it's not so clear what's the role of that South Pole. And you know how it happened. I had a very different and much more technical title. And I was working on my talk, and I ended my work sometime yesterday. And then it turned out that the talk wants this very title that I'm showing you now. Yeah, I had to change the title because the talk turned that way. We'll see whether it works or not, but here it is. So we'll see about the role of that South Pole. I think it will show up in the middle and also in the end of the talk. So let's go to the next slide, which already looks pretty technical. I must say, when listening to the talk of Thomas, I got really scared because I think he almost gave away everything I wanted to tell you. Fortunately, there are still some things which were not mentioned, but well, we'll see. So we start with algebra as promised. And our first topic is SL2 representations. So let me recall that SL2, so these are 2 by 2 matrices, A, B, C, D, with a determinant AD minus BC equal to 1. And those 2 by 2 matrices, they act on the 2-dimensional space C2. So we send a pair Z1, Z2 to the matrix A, B, C, D, acting on the 2-dimensional vector. Or maybe in more detail, you see I put there those formulas that Z1 goes to AZ1 plus BZ2, and Z2 goes to CZ1 plus DZ2. So this is still somewhat complicated, right? Because it mixes Z1 and Z2. And also on the one hand, and on the other hand, maybe we want something more complicated as objects than just Z1 and Z2. And we can look at polynomials of degree D. So here I wrote for you a basis of those polynomials. They are Z1 to the power D, and then you can shuffle. Instead of 1Z1, we can have Z1 to the power D minus 1, and you can add in Z2, and so on. So in total, there are D plus 1 of them. But now I will act on them by matrices which are diagonal, which are simpler than just a general A, B, C, D. And then if the matrices are diagonal, then the unit determinant condition tells us that the left upper corner and right lower corner, that they should have matrix elements opposite to each other. So something like what you see on the slide, Q0, 0, Q minus 1. So then if you act on your Z's, so you see that all those monomials, they are multiplied by some multiples, Q to the power D, Q to the power D minus 2, and so on, Q to the power minus D in the end. I'm not sure, do we see the whole slide? Or down there, there is also some, I think I also wrote that the dimension is D plus 1. Okay, good, thank you. So now maybe we go to the next slide, and remember Thomas in his talk mentioned that one can look at the important features of representations called characters. Now the character is simply the sum of all those multiples. Remember on the previous slide, there were those multiples, Q to the power D, Q to the power D minus 2, and so on. And now we sum them up. Well, if we sum them up, it's an easy exercise because it's a geometric progression. So there is a simple answer to it that I wrote there, q to the power d minus q to the power minus d minus 2 divided by 1 minus q to the power minus 2. So these are characters of those SO2 representations. For us, of course, most of you, or the grand majority of you, know very well what they are. In case you don't, maybe I'm thinking of my family, well, this is just the sum of that geometric progression. Now, let's do the following. Let's even specify Q to be something easier, not just any complex number, but an exponential of some phase. So a complex number with absolute value equal to 1. So then, again, I can substitute it into that geometric progression formula, and there is a beautiful ratio of two sine functions. So the sine in the numerator, it has an extra d plus 1 under the sine, and the sine downstairs is simply the sine of this psi over 2. And this is a particular instance of the famous Weil character formula, which gives characters of irreducible representations of finite dimensional simple Lie groups. But we're only concerned with this particular formula. Now, we're going to play with it in some relatively strange way. Let's go to the next slide. So here there is a notion of scaling. You know, by the way, oh, I'm so sorry. In principle, there were colors in my talk, but well, now it's black and white. Well, what to do about it? So, so scaling. Let's do the following. Remember that d was the degree of those polynomials. If we multiply them by some large positive integer k, well, we can do that. And let's at the same time divide the parameter psi by the same integer k. So we get a new combination. So the degree is scaled and also the parameter is scaled, but in the opposite direction. Then we can ask, how does this character behave when k is large? And it turns out that there is a leading contribution that you see on the right-hand side. So this leading contribution is proportional to k. So when k goes to infinity, it blows up. And then, well, for some reason, you will see why I decided to put k over 2 pi in front. And then the coefficient does not depend on k now. It is this funny expression, sine d xi over 2 divided by xi. And then there will be some sub-leading terms. So we are only interested in the leading term. And let's ask the following question. What is the meaning of this expression? So what is the meaning of the coefficient? And remember, according to the first part of the title, we are supposed to travel from algebra to geometry. Now we've done our first movement in algebra, and now we're going to see what corresponds to it in geometry. So let's go to the next slide. And now I'm doing for you some small exercise of integrals over a sphere S2. Let me first remind you some simple fact from Euclidean geometry. So if you have a round sphere, so I tried now here to draw. So there is a round sphere of diameter d. And you know, of course, there is a little bit of confusion because I denote the diameter by the same letter as the dimension, but it's intentional. And I introduce those cylindrical coordinates. So one coordinate will be the coordinate z, which is just a vertical coordinate. And the other one is the angle phi, rotation around z. Then it turns out that the area on the sphere is equal to the product of d phi dz. In fact, this is slightly wrong because if you're a Riemannian geometer, you would also multiply it by the radius of the sphere. But here we prefer to do some other type of geometry, symplectic geometry. So there, this would be the correct expression, but doesn't matter so much. Up to a constant, that's how it looks like. So maybe just to remind you some simple but amazing fact, that if you take a column between some values of Z1 and Z2, then its area does not only depends on the difference between Z1 and Z2. It does not depend on where you are on the sphere, near the pole or near the equator. So that's one of the consequences of this formula. And we're going to look at the integral of the exponential function. And again, I put psi as a coefficient in the exponent, and it's not a coincidence, because if you compute it, so here I do this very, very simple elementary computation for you, integrating first over d phi and then over dz, then we obtain exactly the same expression that we saw on the last slide. If we could briefly revisit the last slide, just for some seconds. Could we go back to the previous slide? Thank you. So you see this coefficient here, it had a value of 4 pi times the sine divided by xi. And now if we go down to the next slide again, so here, miraculously, this integral is just equal to the same expression. Could we go to the next slide? So you see, as you can imagine, this is not really coincidence. This is one of the manifestations of the orbit method invented by Kirillov and developed by Constant and Suryo. And it was mentioned in Thomas's presentation. So it kind of gives you a dictionary or a correspondence between representations and geometric objects called coadjoint orbits. Now those two spheres are particular examples of coadjoint orbits. And in particular, you know, the characters or the things that we were thinking about representations were the dimension and the character, and about the two spheres, the diameter and those orbital integrals of exponentials. And in fact, there are names for going from algebraic part to the geometric part and back. And when you go from geometry to algebra, on those occasions, it's called quantization, this operation. And when you go from algebraic objects to geometric objects, this is called classical limit. In fact, what we were doing with you now, that was a classical limit, right? We looked at the characters, we introduced some kind of funny asymptotic regime where the dimension gets very, very big and the parameters get very, very small, and then we discovered orbital integrals. So if we go to the next slide, we can discuss it a little bit in more detail. So, you know, it turns out that it's related to some great discovery in geometry. I here call it the Duistermaat-Heckman miracle. You can also say it's sometimes it's referred to the Duistermaat-Heckman theorem or Duistermaat-Heckman localization. So they discovered it in particular cases of orbital integrals, and then it was understood by Berlin and Verne and by Atiyah and Bott in a much more general and conceptual setup. But what happens with our two-sphere? So note that we have a two-sphere, and it has famously in geography, you probably had it in your lessons in geography at school, a two-sphere has a north pole and a south pole, right? If you think of rotations of the two-sphere around the vertical axis, these are exactly the fixed points of those rotations. Now, both in geography and in mathematics, we like to consider maps. And now I'm drawing to the right of the sphere, I'm drawing to you those small maps. near the North Pole and the South Pole. And if you think how the Earth rotates, so then you see that near the North Pole, it rotates counterclockwise, and near the South Pole, it rotates clockwise. And we assign to it a number, this W, which is +1 for counterclockwise rotation and -1 for, +1 for anti-clockwise and -1 for clockwise rotation. So then you see, then down there, I'm doing some very, very elementary transformation. I'm just transforming the sign into the sum of two exponentials with a sign. So the sign is exactly +1 for the first one and -1 for the second one. And the Duhamel-Hackman theory, actually, it gives you the whole class of integrals that you can compute exactly by contributions from fixed points of circle actions, or in more generally, other torus actions or actions of, in more general theory, non-abelian compact groups. But for us, S1 today would be quite enough. And you see there are two contributions. So the first exponential, that's the contribution of the North Pole. And the second contribution is a contribution of the South Pole. So W stands in the denominator, and in the numerator, you have an exponential which has a value of the Z coordinate, d/2 for the North Pole and -d/2 for the South Pole. By the way, so remember there was that South Pole in the subtitle. Now we meet it for the first time, and here, well, it's just there, right? You don't need to search for it. It's apparently on a two-sphere, there is no problem with finding the South Pole. Of course, historically, it took a great effort for people to go there, but for us now, mathematically, we just see where it is. So that was the first part of the talk. So I presented to you some really simple, but really very, very significant example on the relation between algebra and geometry. And here our idea was to start with some algebraic story and to go to the geometric story, which actually turned out to be quite exciting and interesting, even though the example that I presented is very elementary. So now we'll switch gears and we'll pass to another story where we'll start with some geometry, and then we'll have to look for algebra to explain it. And this is the story that I was interested in already quite some time ago, maybe even around 30 years ago, in collaboration with Samson Shatashvili. We were looking at some infinite dimensional analogs of this situation. And I must say, so we were able to do something that time, something very interesting. Now there is a new wave of interest, especially in physics, so people are interested in that story. It has like a big development nowadays. I will briefly mention it, but not in detail. And I will show you one new simple result, and I will show you there are many open questions. I will show you one open question about the South Pole. So if you go to the next slide. So you see, that's an infinite dimensional example. And one of my motivations to talk about it today, because it's about the Schrödinger operator. Of course, Schrödinger operator, that's the whole universe. There are many, many things about it. And we're looking now at a very, very simple example. Well, I didn't put in various physical constants. So for me, the Schrödinger operator is just minus the second derivative plus the potential. And I would like this potential, so everything is happening to start with on a real line. X is a coordinate on a real line. And my potential, I want it to be periodic. So there are two possibilities to look at the story. We can think of it as an operator with periodic potential on R, or an operator on the circle. I prefer to think today about an operator on the circle. So V of X is the kind of nice potential, and we're looking at the Schrödinger operator on the circle. So if you go to the next slide. So remember, so we were looking before, our first example was a two-sphere. A two-sphere, why is it good? Because you can rotate it, right? A sphere is a geometric object with a lot of symmetry, right? And it's a coadjoint orbit actually of the rotation group, either SO3 or SU2, whatever you prefer. Now, there is also a huge group acting on the circle. This is a group of reparameterizations. So we're sending the parameter x to f of x. We want f to be monotone, having, say, positive derivative, and we want it to have this periodicity. So these are diffeomorphisms of the circle. F of x plus 2 pi is f of x plus 2 pi. And it turns out that this group acts on Schrödinger operators. It's not obvious how it acts. If you simply reparameterize, then the first derivative will show up. In fact, you have to conjugate your Schrödinger operator so as to get rid of the linear term in derivatives. But the outcome is as follows. So the potential is transformed by reparameterizations in this kind of complicated way. So the potential is multiplied by the square of the derivative of f, and there is an extra term, this s of f, this so-called Schwarzian derivative, which you see, it kind of looks frightening. So this is the third derivative of f divided by f prime minus 3/2 of f double prime divided by f prime squared. So that's a famous and complicated and interesting expression. And well, that's what replaces rotations in this case. So remember, sphere with rotations, and now those Schrödinger operators on the circle, which are kind of transformed by reparameterizations. Let's go to the next slide. And here is the question. Define and study the integral over the group of reparameterizations of the following expressions. So exponential of ixi, and here I put an integral over the period from 0 to 2 pi of the potential. So the exponential, that's something easy that really reminds us of the integrals that we saw on the two-sphere. Remember, we had an integral of I xi times z variable, and here this integral from 0 to pi, it replaces z. So here, nothing complicated happens. Of course, what is very frightening is this integral over df. Those integrals typically do not exist. So here, well, we'll discuss on the next slides what we can do about it. But let's say that's a wish. And this wish, instead of explaining to you what it is and so on, let me say why it is useful or important. That's because those things, they come up in many mathematical and physical topics. So let me just list some of them. These are symplectic geometry. In this case, would be infinite dimensional symplectic geometry. And Teichmüller's theory, because it turns out that this is related to the theory of the Teichmüller space and complex structures on surfaces. Related to it is actually the field which is called 2D gravity. And that's how Samson and I got interested in those topics 30 years ago. Nowadays, the developments come from condensed matter theory, surprisingly. So some topic in physics where those expressions come up. And then, well, of course, where there is 2D gravity, string theory is never far away. So in any event, if we could really make sense of this object, if we could really understand it well, there would be a lot of common good for many things. So let's see, of course, I will now present you some very tiny piece of thinking about this problem, but we'll see what comes up. So if you go to the next slide. Well, remember on the two sphere, we had this idea that the sphere, of course, you can rotate it as you want with rotation group, SO3, but we singled out the rotation by the circle. And similarly, among all those reparameterizations, there is a circle action where f of x is particularly simple. Simply f of x is equal to x plus theta. We're simply rotating our circle. Now, remember, it was important to know what were the fixed points. Here, the story is very, very easy. In fact, maybe too easy, as we'll see. And you know, if the potential doesn't change when you rotate it, this means it's a constant, right? So typically, among all those f's, if you want something to be invariant under rotations, there will be only one. There will be only one solution. So on the sphere, there was a north pole and the south pole. Now there is only one constant. If you transform this constant with arbitrary f, which is not just a circle action, so then you will never get a constant, it turns out. Of course, that you need to prove, but that's a relatively easy thing to see. So then remember, there was this W. Now W will be on the one hand some more complicated thing. You need to take a differential operator, the derivative over x. In fact, here I think instead of tau I should have used psi. Unfortunately, I cannot correct it. But I guess so far in the talk you will not be too critical. So this W will be Pfaffian of some differential operator. Fortunately, there is a relatively standard theory of zeta function irregularizations, which tells you that this Pfaffian is a relatively simple thing. The square root of 2 pi divided by I tau, or I psi would be a better name. If you go to the next slide. So now we can simply assume that the Dustermath-Heckman theory works. Remember, Dustermath-Heckman's theory was telling us that to compute such an integral, we should simply look at contributions of fixed points. Well, now there is only one fixed point. So what happens there, this integral of a constant is equal to 2 pi times that constant v. And that's why you have that exponential. You know, I'm just computing the expression under the integral at the point. So that's the magic of Dustermath-Heckman localization. And the expression in front, that's 1 over w. So that's simply this expression that we saw on the previous slide. And actually, that's what Stanford and Witten, maybe 2-3 years ago, they advocated for this answer, that this integral is well defined and gives this particular answer. Now, you know, Thomas mentioned that I started my career as a physicist. That was long ago. And then I went to the dark side, or I went to the good side. I don't know how to interpret it. I turned to mathematics. And then for a mathematician, of course, you ask a question, what does it really mean, right? But I mean, okay, the left-hand side doesn't make sense. The right-hand side is very well defined. It's a simple, rather well-defined expression. Now, well, the question is, what does it really mean? If you go to the next slide, here is the beginning of our attempt to understand it. You know, and it's based on some infinite dimensional object, the Virasoro algebra. That's a centrally extended Lie algebra. It has an infinite number of generators. It has a central generator C, and the defining relations are written there. So the representations, remember, so we're now getting back to algebra again. So we started in infinite dimensional geometry. but you see infinite dimensional geometry, that's a tough topic. As a mathematician, I don't understand it very well. So, and here algebra comes to rescue. So representations of the Virasoro algebra are classified now by two numbers. Before, for SO2, we had one number D. Now there will be two numbers, the so-called highest weight. I write it as C and L naught, whatever that means. And maybe if you go to the next slide, remember, we have to look at the characters. In most of the situations, the Virasoro characters, they're given by this both simple and complicated formula. So remember, there is again a parameter Q. I don't explain too much what it is. That's a similar story to what we had in SO2. Character is typically a function of Q. So it's a Q to some power, which depends on the weight. And then in the denominator, there is this infinite Euler product from 1 to infinity, 1 minus Q to the n. So that's because now the story is infinite dimensional. There are some relatively complicated objects coming up. Now, well, you know, from the SO2 example, we know what to do. We replace Q by the exponential of some angle. Now you see I kind of, now I again denote it by Xi. So sorry for this notation problem. And we do the scaling. So the weight, so the analog of D, you multiply it by a big number. Xi, you divide by a big number. So, I mean, right, we basically know what to do. So the question, what happens? And well, let's see what happens on the next slide. So, and that's a small theorem that we proved with Samson. So you again want to see how this expression behaves. It consists of two parts, and actually there should be plus dot dot dot. And you know, if you look at the second line, the expression, the first expression, the kind of infinite expression on my original slide, it was supposed to be in red because it's infinity. Remember before it was for SO2, it was divergent like K. Now it's an essential singularity. You see there is some exponential of pi K over 12 Xi. So, and that's the essential singularity which is controlling this classical limit. So classical limit is almost always singular, and that's how the singularity now looks like. And then the leading coefficient in front of this essential singularity, if you look now at the right side of the formula, which was supposed to be beautiful in blue, please imagine it. So this is exactly the expression that we saw before. This is the Stanford-Witten formal integral. So if you look at it again, if you return to the previous slide, and maybe to the one before, and maybe to the one before, thank you. So that's exactly this expression where tau should be replaced by Xi. Okay, so far so good. So you see, it turns out that infinite dimensional algebra comes to rescue of infinite dimensional geometry. It gives us an understanding, or one of the possible understandings of this formula. Now let's go to the next slide, and then to the next slide, and then to the next slide. And I would like to finish my talk with an open problem. Actually, there are many open problems in the field, but let me just state one of them. You know, I said that most of the representations have characters, as I showed you before, but not all of them. So for some special values of C and L naught, that's a very, very beautiful theory, which also interacts very well with two-dimensional physics. But you know, okay, for some special values of C and L naught, the character looks differently. Actually, that's not the only way how it can look like, but let's say that's at least the first more complicated case. And you know what happens? The expression is almost as it was before, if you still have a memory of that, q to some power divided by that infinite product. But now in the numerator, you have 1 minus q to the m. So this means one of the factors in the denominator is absent. Now, after scaling, what the thing that will happen is that you see it down there on this slide. And well, it looks like some infinite expression, again, the same as we had before, times something which looks like a sum or a difference of two Dustermath-Heckman contributions, right? So this is, each of the terms is an exponential times 1 over Pfaffian. So it looks like, of course, now it's infinite dimensional story. So there are two fixed points for S1. So from there, we read the value of the integration function at the fixed points. The Pfaffians turn out to be the same. So the natural question is, what is this space? The interesting or bad or good or, I don't know, news, excellent news, horrible news is that the theory of Schrödinger operators on the circle that we looked at before absolutely does not provide spaces with this property. Remember, we said that S1, it always has just one fixed point, it's a constant. And then if you apply reparameterizations to the constant, you never get another constant. Now, algebra is telling us that the classical limit has 2 points. So we easily discovered with you the North Pole, or relatively easily, in the Schrödinger story, but the South Pole is not there. And well, we need to discover it. So I would like to end with that question. That was the cryptic subtitle of my talk. So we're still on the search of the South Pole. I hope that, well, sooner or later we'll report on the success, and or maybe some people in the audience report on the success. But you know, geographically, it did take some effort, and it was difficult to discover the South Pole. So hopefully we succeed sooner or later. And I thank again the Schrödinger Institute and everybody for participating in this event. Maybe if you show the next slide. So that's the thank you slide. So thanks a lot. And that's the end of my talk.
Thank you very much for this beautiful talk that took us from algebra to geometry and then back to algebra. Thank you also for sharing your recollections of the early days of the Erwin Schrödinger Institute. So I would like now to again congratulate you for all your scientific achievements, and of course for the ESI medal, and I would like to ask you to join me in a big round of applause.
Thank you very much. Thank you, everybody. It's a very, very important moment for me. Thank you.
Thank you. So I will now give the microphone back to our musicians. Thank you, Teresa Kalkhauser and Wolfgang Augustin. This was very beautifully played again. Thank you very much. So this brings us to the end of our program this afternoon. Normally, I would invite all of you to the ESI common room for some refreshments, but unfortunately, we cannot do that today. I hope that times will be better. I'm sure that times will be better at some point, and then we can meet here at the ESI again. So let me thank you for spending this afternoon with us. And take care and stay healthy. Thank you. Thank you, Anton, and goodbye.
For being with me today. Thank you.